Swayam Prabha. Digital India. Educated India.
Welcome back to my course Industrial Biotechnology. Now in the last lecture I discussed about the enzymatic reaction kinetics, and basically I told you that enzymes they are very specific as per substrate is concerned, because I told you that as for example glucose isomerase can act on glucose and produce the fructose. It cannot act other than glucose. So they are very specific. Protease acts on protein molecule to degrade the protein. Lipase acts on lipid just to degrade the lipid molecule. So they are very specific as per substrate, and this kinetics of the enzyme degradation, that is explained with the help of Michaelis-Menten equation. And then we discussed different inhibition kinetics. We have competitive inhibition, we have non-competitive inhibition, we have uncompetitive inhibition, and now in this lecture we want to go little bit ahead, because when we want to carry out any kind of enzymatic reaction in kind of reactor, and how you to produce some kind of product, how we can analyze the system. So this I am going to discuss here. Now first I want to tell, I told you that that as the processes are concerned, there are two type of process we have. One is batch process, another is continuous process. Now if you look at this enzymatic the batch process, particularly batch process is considered is the unsteady state operation. Why it is unsteady state? If you look at the substrate concentration with respect to time, it will keep on decreasing with respect to time. As we know the rate of substrate degradation, this is proportional to the substrate concentration. Am I right? Now if the substrate concentration keep on changing, naturally rate of reaction is changes. So it is a example of the unsteady state operations. Now this is now I told you, when you do any kind of reactor analysis, we use a formula. What is this formula? Rate of input equal to rate of output plus rate of consumption plus rate of accumulation. Now here in case of suppose this is the batch process, there is no input, there is no output, so we can write this is equal to 0 and this is equal to 0. What is the consumption? Rate of reaction into V, because rate of reaction is ds by dt. ds is the concentration mass per unit volume. If you multiply it by volume, then you will get the total what is the rate of change of the substrate molecule that is there, and this is the accumulation, S into V into dt. This is called accumulation. So this is how we explain here. ds by dt is considered minus V. This is because why is minus? Because substrate concentration keep on decreasing with respect to time. So it is, since it is decreasing, this minus sign has come. But at the same time, when you have product formation, then this will be, if you write dp by dt, this always will be positive, because when you talk about the ds by dt, this will be negative, because this is the decreasing profile, this is the increasing profile that we have. Now here you see that that how we analyze the system, that we can have this here, this so what you can write here, the minus rs into V equal to dsv by dt. Am I right? And now here that if you look at here that your V equal to V max S Km plus S. Am I right? Now what we can do, this is equal to this is a minus ds by dt. Now I can bring it here that we can exchange like this, and if we exchange, then we'll come across the we can come this kind of equations that km, this km plus s by s into ds. So this equation will come. Will then if you analyze this, this will be km into ds by dt. This is s and this is like this, and then ds, this is ds by s. ds by s is what? ds by d ln s. Am I right? Now if you integrate s0 to s, then what will happen? ln s by s0. This is how it is coming here, s by s0, and ds equal to s minus s0, because this is then this is minus, this is the 0 to dp, dp is the batch per time, and then if we analyze, then we can find the time of the batch reaction can be expressed by this equation. So this is very simple. We can monitor that you suppose from this equation we can find out, suppose we want to find out the 50% time required for 50% substrate conversion. How you can find out? So you write this s equal to 0.5 into s0, this is 0.5 into s0. So if you know s0 value, you can find out that what is the time required for the batch fermentation process. You can easily calculate. Now the one drawback of the batch process is that after the batch is completed, then you have to restart the second batch. And for that, what you have to do, there is the important that things that will come in the picture called downtime. So suppose this is the batch, am I right? This is the batch, and this is the fermenter, and you carry out the fermentation. After the fermentation is over, you have to take out the material. Again, you have to clean the vessel and refill the substrate here. Am I right? For that, you require some time, and this time we consider as the downtime. So whenever we talk about any kind of batch fermentation process, we still have to consider the total batch time. Total time is the total batch time, reaction time is the time required for the reaction to carry out in the batch process, plus downtime. So this downtime we have to consider in case of batch fermentation process. This we shall have to remember. Now at the end I shall solve some kind of numerical problem. When you solve the numerical, your idea on this that particular things will be clear. Now let us see how we can operate the continuous process, because in the enzymatic reaction, how you operate in a continuous process. The problem is that we have well starred reactor. This is like this. This is the reactor that we have. We can this is here there is a continuous inflow and continuous outflow of the reactor. And what is the purpose of the agitator? Make the homogeneity of the reaction mixture. So what I want to point out here, suppose whatever substrate concentration is there, the same substrate concentration, because since the concentrate that this is the homogeneity in the reaction mixture, the concentration should be same. The only the problem with that, in case of freely suspended enzyme, when there is a flow, the enzyme present in the reactor that also leaking from the system, that will go out with the liquid. So if we don't add any kind of enzyme, then what will happen? A time will come when there is no enzyme present in the reactor. So your total reaction will be stopped. So this is this kind of problem that we have during when we talk about the suspended enzymes, enzymatic reaction by using suspended enzyme. Now then let us see how we can analyze this system. Now actual that dilution rate, I already we might be knowing that dilution rate is what? The flow rate. This is volumetric flow rate by volume. What is the volumetric flow rate? Volume per unit time. Am I right? And what is this is volume. So what is happening? This volume will cancel. So what will be the unit? 1 by time. So dilution rate, what is the unit of dilution rate? Is the time inverse. But hydraulic retention time, what do you mean by hydraulic retention time? That this is 1 by d. 1 by d equal to time. That means, suppose you are passing the liquid through the reactor, the question is that how long this liquid resides in the reactor. That is the called hydraulic detention time. So, this is how we can calculate here. Now, here also we have the material balance like input plus generation equal to output, consumption and accumulation. Now, here the substrate balance we have under steady state condition that F into S0 is the input that we have, this is F, this is S0, and there is no generation because substrate is always consumed. Then output is the F into S, this is F into S. Then consumption is minus Rs and S. Now, if you consider the steady state, I told you that what is steady state? When the concentration is remain unchanged with respect to time. Then when how it is achieved? When the rate of accumulation of the substrate is 0. If your accumulation substrate is there, then it is not possible to attain the steady state condition. So, your accumulation this should be equal to 0. So, if we analyze this process is coming like this, F into S0, F V is the velocity and capital V is the volume of the reactor, and final equation will be D into S0 V max S by Km plus S. And this equation can be used to calculate the dilution rate required to achieve a particular level of substrate conversion. Suppose we want to achieve the 50% substrate conversion, 80% substrate conversion, that this equation we can use that how we can achieve that particular conversion and how much time is required, that also we can calculate from that. How we can calculate the time? I can tell you that that also we can. I have already mentioned what is the T equal to V by F. Am I right? V by F equal to 1 by D. So, if you so this is the volume of the reactor, this is the particular volumetric flow rate, and if we find out the time of the reaction from this particular process, then we can easily find out the volume of the reactor. Now, in case of plug flow reactor, that and what do you mean by plug flow reactor? That it is like this. This is the liquid is flowing like this through a particular tube. Tubular is the kind of tubular type of reactor. So it flow like this. Now, plug flow means that in a true sense, ideal plug flow, there should not be any kind of velocity gradient across the cross section of the tube. This is called in case of ideal plug flow. Now, it goes like this, that one and two others. Now, if you look at, suppose this is the S0 and this is S, the S0 with respect to distance, this keep on decreasing with respect to time. So, that means your substrate concentration and different parts of the reactor, that will be different. So, at different distance you have different rate of reaction. It is something similar to the batch process. What is the batch process? Batch process is substrate with respect to time, it is decreasing like this. And here in case of plug flow reactor, this substrate concentration that decreasing with respect to distance. But here one thing is that there is no axial mixing. Axial mixing means when it goes like this, there should not be axial this side axial mixing. There might be the radial mixing. Radial mixing is permissible, but axial mixing is not possible. Axial mixing actually takes place in case of CSTR. The composition varies along with the flow path, that I have already explained. Now, this is kind of example that we have. Suppose this is, I told you this is F into S0 and this is M into S. Now, to analyze the system, we initially considered a differential fragments. This is a differential fragments whose thickness is del Z, and so this is the, if you know the cross sectional area A and del Z, this will be equal to volume of the del V. Del V means volume of this particular differential section. Now, if you want to do the mass balance across this particular differential section, again our equation is same, input equal to output plus consumption accumulation. What is the input? F into S into Z, this is the Z step action, and whatever change is there I can write Z plus del Z, and then this minus RS into this volume, because that we can express like this. Now, here you see that this is F into S Z plus the del Z plus S, and this is the volume A into del Z. Now, here what is happening? This is a flow rate. Flow rate is what? Volume per unit time. Am I right? And this is what? This is the volume. Now, this is A is the area. Now, if you divide by area, then volume divided by area will be, then this will be velocity. This is called velocity. This is U is the velocity, and the del Z is the thickness of this particular strip, and this we can analyze and we can have this equation. Now, finally, we will come across this equation. This is 1 by U equal to del Z. This is the strip that because this is what we are planning to do. We have analyzing across this strip. This is equal to del Z. So, if we know the del Z and we can integrate 0 to L, this is whole length. Then we can have we can take care whole volume of the reactor. So, this is how we can do this. That this is equal to L. And this whole strip is now. If you look at this this equation, that this is that U, if you U by L, U is the velocity, L is the length. Then this will be equal to U, the time inverse. Am I right? And L by U is the time. So, tau plug flow reactor means space time in the plug flow reactor. How long the liquid remains in the reactor to convert S0 into S, that can be explained like this. Now, if you look at this expression and the batch expression, that is, we will find almost that is same. So, we can write the space time of the plug flow reactor is same as the time required for the batch process, because T batch equal to T tau plug flow reactor. Now, this is the problem I told you at the beginning, that we want to solve a numerical problem, and if we understand the problem correctly, then I hope that the conception of this reactor analysis will be very much clear to you. Then try to understand. Now, what is this problem? Problem is that glucose is to be converted to fructose by using the glucose isomerase enzyme. So, you know that you have a reactor like this. You have a reactor like this. So, here we are bringing the glucose, and what enzyme we are giving here? This is glucose isomerase. Glucose isomerase enzyme we are giving. This is the reaction, that this is the hesitator reaction takes place. The initial glucose concentration is 200. So, S0 is 200 grams per liter. Am I right? The degree of conversion is 60%. So, we want to produce 60% conversion of the substrate. So, what you have to do, that we want to produce 10 kg of fructose per day from glucose by using glucose isomerase. So, what should be the volume of the reactor in the batch process? CSTR and plug flow reactor, and the kinetic constants are given. Vmax is this much, and Km value is this much. The yield coefficient means, that is Y P by S is the yield coefficient, means gram of product formation per gram of substrate consumed. This is 1. That means 1 gram of glucose gives 1 gram of fructose, and downtime is considered as the 4 hours, and activity of the biocatalyst can be assumed to be constant in time. So, this is the couple of assumptions we have made. Let us see how we can solve it. Now, this is the stoichiometry we have. The glucose, 1 mole of glucose in presence of enzyme produces 1 mole of fructose. Now, these are different parameters are given. Now, we have already seen the T batch. What is the T batch? T batch equal to minus the tau S0 by S ds by minus Rs. What is minus Rs? Rs is the velocity of reaction. What is the velocity of reaction? Vmax by S Km plus S. Am I right? And this is the we have by integration we have already found out this expression that T batch equal to 1 by Vmax K minus Km ln 1 minus Xs into S0. This we can easily find out. And Xs, what is Xs? Is the fraction of substrate that is converted. Xs equal to S0 minus S by S0. So, here 60% converted. So, that means what will be? This is 0.6. Am I right? So, this is 0.6 that we have, that we can put it here, then we can find out how much time is required for the batch process. We can easily calculate that. Now, here again I told you that one of the drawback of the batch process is the downtime, because when you run the batch, you have one after the completion of one batch you have to run another batch. So, naturally that you require some time, because you have to take the material out and you have to clean the vessel, again refill the vessel. So, for that you require some time, then that we consider as a downtime. So, that downtime we have to consider. So, here we have already find out that suppose we find out this is 2.307 hours, and but you have downtime is 4 hours. So, total time of the batch process is coming how much? 6.307 hours. Am I right? Now, when you operate any kind of, suppose we want to find out what is the volume of the batch reactor. So, what you have to do? We have to find out that how many batch you have to operate per day to get the desired amount of product. Now, so this is the one batch is required 6.307 hours. The one day is 24 hours. Am I right? The number of batch per day we can operate how much? 3.880. This is the number of batches we can operate. So, now if you look at the problem that our basis was 10 kg of fructose we want to produce per day. Am I right? That means 10 kg per batch, how much we can produce? 10 divided by 3.8, that is 2.863 kg. This is per batch we shall have to produce. Am I right? And then then we know that our yield of substrate is the 1 kg of product, yield of product is 1 kg of product can produce from 1 kg of substrate. So, how much substrate is required? Then since it is 2.63 kg of product, then our substrate also required 2.63 kg of substrate. Now here we have 60% conversion of the substrate. So, we can divide by 0.6360, then we find out this is the actual amount of substrate required for this fermentation process. Now, then question comes, what will be the volume of the reactor? The actual amount of substrate required, is how much? 4.38 kg. And what is the initial concentration of substrate? 200 kg per cubic meter. So, our volume is coming 0.022 cubic meter. This is equal to 22 liter. We know 1 cubic meter is equal to 1000 liters. Am I right? Just you multiply that 1000, you will get the 22 liters. So, what I want to stress here is very simple. It is easy to calculate that volume of the reactor. What we can do that. First, again I am repeating it again, that if you look at the batch process, first we do what you can find out, we shall have to find out the time of the batch process. Once your time of the batch process is done, then you have to find out that total time required for the batch process, that the batch process plus downtime, and when you have the total time, then you find out number of batches per day. Then once you know the number of batches, then you find out that how much product you have to produce per batch, that is 2.63, and you know when you have the stoichiometry, that for getting this much of product, how much substrate is required, then you can easily find out how much substrate is required. And since you want to have 60% conversion, so you can easily calculate how much product is required, how much substrate is required for this process. Once you know that how much substrate is required, then initial substrate concentration you divide, you will get the volume of the reactor. So you can easily calculate that. Now let us come to the CSTR process. Now in the CSTR, what we have like this. We have continuous inflow and outflow, and our expression that we have already developed, that is tau CSTR, because the tau CSTR is equal to S0 minus S by minus RS. This is how we can write. Now this can be simplified in this form. If the RS is the velocity of reaction, you put this value, you will get this equation, and then you put this value that you can remember. I can little bit elaborate here from the material analysis. You see, I have shown. You can, if this is equal to V equal to minus ds by dt into V. Am I right? This VB will cancel. So it will be, what we will be having, the dt equal to, I can write like this. I can write dt equal to, I can write ds by minus rs, and this is only S0 minus S minus rs. So this, how this has come, that there should not be any confusion how it has come. So this is how it has come. Then we know that velocity of reaction equal to minus rs. This is equal to Vmax S Km plus S. So you can put this value in this equation, and we can find this and the expression, and you put the values with 60% conversion of the substrate, and here time is coming around 2.63 hours. Now here, in a advantage of the continuous process is that there is no downtime. No downtime is required in the continuous process, because you continuously you can operate. Now let us see how we can find out that that volume of the reactor. How we can find out the volume of the reactor? Now volume of the reactor I can write like this. What we can write, tau CSTR equal to volume of the CSTR by F. F is the volumetric flow rate. So it is like this, that tau CSTR is equal to volume of the reactor divided by volumetric flow rate. This is volumetric flow rate. The volume will cancel, so this will be time. Am I right? So here this is so what you have to find out, that what is the flow rate. Now here, how much product you want to produce? 10 kg of product you can produce. For 10 kg of product, how much substrate is required? 10 kg. Now what is the percentage of substrate conversion? Is 60%. The 10 divided by 0.6, that is, this is the actual amount of substrate that is required. So if you, then you can convert it. This is in hours, so you can, if this is per day, so you divide by 24, then you will get the 0.7 kg of substrate you require per hour. Am I right? So now this is the what is the actual amount of substrate? 0.7, and this is the, what is the initial concentration is 200 cubic meter per hour. So if you do that, then what will happen, that we can easily find out what is the volume required for this. That this is the concentration, kg per cubic meter. This is 200 kg per cubic meter, and this kg will cancel, the cubic meter will go up. So, it is cubic meter per hour. So, this is coming like this. Now with that volume of CSTR equal to F into tau CSTR. So, 3.6 into this, so this volume is coming around 8.26 liter. So, this you can do it very, again I am telling you how we have done. Initially we consider 10 kg of fructose per day, and we take the yield coefficient that from the stoichiometry we can easily find out that for producing this much of product how much substrate is required. Then we find from the stoichiometry 10 kg product formation, 10 kg substrate required, but your conversion efficiency is 60%, you divide by 60, you find out the exact amount of substrate that is required then per day. Then you will find out that per hour how much substrate is required. The volumetric flow rate you have to calculate for this equation, and that can be determined by this, that actual substrate requirement, that is 0.7 kg per hour, and this is initial substrate concentration is 200 kg per cubic meter. So, you can find out the volumetric flow rate. Now, you did multiply it with your tau CSTR, you will get the volume of the reactor. So, it is very simple. I hope you can do it. Now, let us come to the plug flow reactor. In case of plug flow reactor, your calculation is similar to as per your batch process is concerned. This equation we have seen, the expression that we have for the T batch and tau plug flow reactor is same. So, here we can put the same value, 60% of conversion, and you can easily find out this, and this value is same. If you this is equal to T batch. If you look at the initial part, then you will find that is the same. But now this tau, when you consider the tau plug flow reactor, now here also what we have, this is volume by flow rate. Am I right? This flow rate you have to find out. Now, we have already shown you how you can calculate the flow rate in the previous problem. Same flow rate you can put it here, then you will get the volume of the reactor. Same flow rate you can find the same value that what we have calculated in case of CSTR. If you do that, you multiply it by that, you will get the this is the volume of the reactor in case of plug flow reactor. Now, if you compare here if you compare this value that in case of batch process how much volume is required, 22 liter. In case of CSTR is 8.26 liter. In case of plug flow reactor is 8.07 liter. So as per reactor design is concerned, when you go for any kind of if anybody asks you which reactor will be suitable for carry out this process, answer should be the plug flow reactor. Now here I want to stress one point, that that in the industry it is obviously the plug flow reactor is always good as for getting your product formation, but I told you that operation of the plug flow reactor is a problem, but there should not be any kind of axial mixing. There should be radial mixing, but there should not. This is very difficult to achieve. So, but most easiest way for operating the plant is the CSTR. Now, question comes, how this plug flow reactor can be replaced by CSTR. So, if you look at what we have done, that this is plug flow reactor. So, this is equal to ds by minus rs. Am I right? This is we have. So, now if you plot this minus 1 by rs versus s, if we plot it like this and it is like this, then here this is S0 to S, the area under this curve, this is we consider is tau plug flow reactor. Tau plug flow reactor, am I right? So, now since it is very difficult to operate, now if you have multiple CSTR, this is like this, then this is 1, 2, 3, 4 like this. So, you have like this number of CSTR in series, this is like this and this is like this. So if they are connected with each other and to do this, there is a possibility that your flask flow reactor can be easily replaced by the multiple CSTRs. Your operation will be easier. So that is why in the industry we usually prefer the CSTR. We don't here prefer the flask flow reactor. Thank you very much.